Hello again, virtual friends. We are now going to study the quotient rule, which is to find, we're going to define q of x for quotient, of course, to be f of x over g of x. So it's some function over another function, and our goal is to find the derivative of said rational function. So what we're going to do is, again, just like I did last time with the product rule, I'm going to present an example so it hopefully gives you some context, and then from there we'll do the abstract proof. It's the kind of thing where, are you going to have to prove this? No. But to truly understand the derivative of the quotient function, it is something that you'll have to understand this more abstract approach. So I'm going to present two functions such that, yes, we could easily divide them and then find the derivative. But then I'm going to do that using the quotient rule, and you'll see that it yields the same result. We'll prove it abstractly, and then we'll do a simple example. So the two functions I'm going to allow here are f of x is going to be 20x to the sixth. G of x will be 4x squared. Thus, q of x is equal to that over that, right? 20x to the sixth over 4x squared, which is the same as 5x to the fourth. And now we know q prime of x is, of course, 20x cubed. So we know that q prime is 20x cubed. Now I'm going to execute this process with the quotient rule. You'll see how it plays out, and eventually will yield 20x cubed as well. So let's take the original two functions, the numerator and denominator, f and g. The first thing we're going to do is take the bottom function, 4x squared. And we're going to multiply it by the derivative of the top. The derivative of the top function would be 120 x to the fifth, right? Minus the derivative, the bottom times the derivative of top minus top times derivative of bottom over the square of the denominator. So this will become 16x to the fourth. And we'll have a shorthand way of writing this as well. The shorthand way is to think of it as low d high minus high d low over low low. Meaning bottom times derivative of top minus top times derivative of bottom over bottom times bottom. Okay? So now if we multiply all of this through, we'll get, let's see, 480x to the seventh minus 160x to the seventh over 16x to the fourth. And 20x to the seventh. And then if we divide these two, we get 20x cubed. And there we are, 20x cubed. So I set this up purposefully so that we had two functions that we could easily divide. But just like with the product rule, what if we have two functions that you can't just so simply divide? Again, like I said before, for example, let's say 20x to the sixth over sine of x. There's not really a simple combining of like terms there that we can do. I use that term loosely, combining of like terms, that we can do and then divide and use the derivative simply here. So we're going to have to use this process. So what I'm going to do now is prove that. It's just similar, the proof is similar to the product rule proof, but maybe it's a little bit more sticky in the details. Remember that what we're trying to end with is low d high minus high d low over low low. So the first thing is q prime of x is equal to f of x, limit as h approaches 0 of q of x plus h, which is f of x plus h over g of x plus h, minus f of x over g of x over h. So I just substituted x plus h into the original numerator, substituted g plus h into the original, x plus h into the original numerator and denominator, and then x into the functions as they were as well. So now we're going to clear the fraction of a fraction situation simply by multiplying through by g of x plus h g of x. So we'll have our limit. This is g of x So what I've done is multiplied that term by g of x plus h. So the g of x plus h has went away, we were left with the g of x. Here we multiplied by g of x plus h, so that we're left with just g of x plus h and the original numerator, and the bottom, of course, got them both. And now, just like with the product rule, we need to come up with a slick multiplier, not multiplier, slick addition and subtraction right here that is 0, but then gives us something useful. So I'm just going to step away, let you think about that. Maybe you want to click pause. We're going to come up with something interesting that we can subtract and add, or add and subtract here, that gives us an easy derivative to take. Okay, so hopefully you thought about that a little bit. Turns out that the best thing to do is this, f of x, g of x. We subtracted it, and now we are adding it. And again, these two terms, here and here, those two terms are 0. So we haven't really done anything bad to the numerator. Okay, now we look for factoring that we can do. You can see clearly that there's a g of x, there's a g of x, so that's what we'll factor out of the first two, and there's an f of x, there's an f of x, and that's what we'll factor out of the next two. So I'm going to resume my work up here. So we'll have our limit, and g of x times f of x plus h minus f of x over g of x, g of x plus h times h, and then add to that the second part with, so I'll just put the limit over here as well, f of x factored out. And then we're left with g of x minus g of x plus h. Okay, you can see on this one, 2g of x's, right? Well, I guess more to the point, I'd rather actually rewrite this thing in what will be a simpler way, I think, for you to see. So what I did with the first term is I just kept the h in the denominator of the numerator, and I left the bottom down here, because that expression right there is f prime, right? And then the same thing I'll do right here. And I'm going to do two things. I'm also going to change this to subtraction, because you can see we have g of x plus h, and we want it to be the other way. So I'll do g of x plus h minus g of x. So negative, negative, that takes care of that. And the g of x plus h was negative, and now it's positive. So I've effectively taken that negative and distributed it in there. Leave that over h, and then put all of it over g of x plus h. So again, this is f prime. This is g prime. So now if I kind of divide that up, we're left with, when h goes to 0, that'll be g of x. Green stuff is f prime, low d high, minus f of x, g prime, low d high minus high d low, over, when h goes to 0, both of these have the same denominator. When h goes to 0, you have g of x, which is g of x squared, or g of x, also known as low d high minus high d low over low, low. So there we have the quotient rule proved abstractly. I understand this is, like I said, the algebra is a little bit more sticky than it is with the product rule, but that's the way it is. And of course, the derivative involves more of a process to take as well. You have to take the derivative of both at some point. You have to square the bottom, and you end up with potentially a more complicated looking function. But that is the nature of the quotient rule. So we kind of made a hand-waving example type argument as to why this thing works, and now we proved it abstractly. And of course, you'll have lots more practice doing this with a rational function or multiple rational functions in your assignment. Okay, thank you.